Okay, so let's see. We want to get to some problems today. So let's get started and get back into this idea of an orthogonal set of vectors, meaning that if you take any two out of the set, they're perpendicular, they're orthogonal to each other. Again, orthogonal, maybe we should add that to our list. And perpendicular are basically the same. So the idea is objects can be perpendicular to each other. Vectors might not be arrows or lines. They could be functions or something else. So we tend to use the word orthogonal in a more abstract way. But your intuition is that there's something about them that they're, you know, in this perpendicular relationship. I don't think you want to lose that picture. So they're mutually orthogonal to each other. That means if you pick any two, their inner product is 0. And then we just ended last time where we started looking at theorem 4. If you take an orthogonal set of non-zero vectors, that has to be a linearly independent set automatically. And let's just think through the proof here, because I think we can follow this reasoning. So I start out when this is going back to the definition of linear independence. If we want to show a set of vectors is linearly independent, one way to do it is suppose we have a linear combination that's equal to 0. We want to show that given this condition that they're orthogonal, C1 through Cp, the weights, the scalar weights, have to all be equal to 0, right? That's the conclusion we're trying to draw in this proof. That's where we're trying to head. And what I say is, what I'm going to do is I'm going to take this linear combination and dot it with U1. That's got to be 0 because, this linear combination is 0 to begin with. Certainly 0 dotted with any vector is 0, right? So we're making that observation. And then what we can do is we can distribute U1 to each one of these terms separately. So we have C1 times U1 dot U1 down the line. But now I picked U1 on purpose here, okay? So U1 dot U1, we don't know what that is, U1 dot U1. But once we get beyond that, U2 dot U1, that's got to be 0 because we have an orthogonal set. And actually, U anything dot U1 is going to be 0 for any of these vectors other than U1 itself. So see the reasoning that all these other dot products, all these other inner products down the line are going to be 0. So we're left with C1 times U1 dot U1 is 0. But U1 dot U1 can't be 0 because U1 is a non-zero vector. So the only way, this is just a product of two real numbers here. This is just scalar times scalar. And since the second factor is in 0, C1 has to be 0. So that's sort of an argument that C1 has to be 0. Now we used U1 to show that C1 is 0. I could go through the same argument again where I put in U2. And the same reasoning will lead us to C2 has to be 0. Do it with U3 all the way down the line to UP. So the way we get away with that here is we just say we can use the same sort of reasoning to show that C2 through CP all have to be 0. So that since all the scalars have to be equal to 0, that's the only way to get that linear combination to be 0. That means the U1 through UP are linearly independent. I think that's a pretty reasonable argument for you guys to be able to follow. Okay, now what's coming up in this box is something we're going to use probably more than just about anything else in the rest of this chapter. This is our first instance of this funny-looking formula. So theorem 5, let U1 through UP be an orthogonal basis for a subspace W of Rn. So we're in Rn. We don't know what dimension. We have a subspace of Rn, so it's not all of Rn. And we have a basis of orthogonal vectors, right? U1 through UP. So P would be the dimension of the subspace. Let Y be any vector in this subspace. Well, we know since U1 through UP is a basis, Y can be expressed as a linear combination of those basis vectors, right? U1 through UP. With real numbers, the weights, the scalars, C1, C2 through CP. And so here's why people care about an orthogonal basis. It allows us to describe what these scalars, what these weights are very explicitly. It turns out for each one, C1 through CP down the line, we have a formula for what that weight has to be. It's the vector y dotted with the basis vector over the dot product of the basis vector with itself. And this is an argument we can, I think, all follow pretty. In fact, it's really short. It's only going to be a couple lines at the bottom and a couple lines at the top of the next page. Okay. So notice we have one of the, there isn't just one of these, right? There's a C1 formula, a C2 formula, a C3, all the way down the line to CP. So we can do this calculation for each one of those scalars. So proof, let's just pick one, pick uj. So pick one of these basis vectors. We're going to look at a dot product again. We're going to take y dot uj. We already said y can be expressed as this linear combination dotted with uj. Now, I didn't write out the detail of the distributive property. We're going to distribute to each one of those terms. And this is an orthogonal basis, right? So uj dotted with any different basis vector is going to be 0. So when we do all these separate dot products, we're going to be left with just one term. All the terms are 0 except one term, the uj dot uj term. And that's going to, that term's going to equal cj times uj dot uj. And now when we turn the page, we're just going to take the first portion of this equation and set it equal to the last portion, and that's basically our result. Let's turn the page. And so again, I just took the first part of that line, set it equal to the last part of that line. These are all real numbers now. When you calculate a dot product, you have a real number. So we have a real number equals a real number times another. I can just solve for Cj. Cj is this number divided by that number, and that's our formula. Okay. Now, I think I want to write a little bit. So I'm going to turn the projector off and screen up, and we'll do this exercise together. So this will be a nice concrete experience. So in the exercise, I'm giving you 3 vectors. U1 is 1, 2, negative 2. U2 is 2, 0, 1. U3 is negative 2, 5, 4. And the first thing we want to show is show that U1, U2, U3 is an orthogonal basis for R3. Okay. And so first, check orthogonality. Orthogonality. Okay. So by that, I'm gonna see if this is an orthogonal set. I'm going to take the dot products of each one of these with all the others. So u1 dotted with u2, what's that equal to? And I'm just going to write this one out in detail. 1 times 2 plus 2 times 0 plus negative 2 times 1. You can think about that for a little bit. That's 0. We actually have 3 to check, right? We got to take u1 times u3 also. I guess I'll write it out. 1 times negative 2 plus 2 times 5 plus negative 2 times 4. That's negative 2 plus 10 plus negative 8. That's 0. So we got to think a little bit about getting every possible combination here. I also have to do u2 dotted with u3, which is 2 times negative 2 plus 0 times 5 plus 1 times 4, which is 0. So thus, u1, u2, u3 is an orthogonal set. Now we've got to show that it's a basis for R3. Well, u1, u2, u3 is a linearly independent set by theorem 4. Just look on the previous page. Any orthogonal set of non-zero vectors is linearly independent. So we don't have to show linear independence. That follows from that theorem, right? That's the power of this orthogonality, right? It takes care of that. You gotta say non-zero because you could have an orthogonal set with the 0 vector in it. I don't know why anybody would want to do that, but there's no way a set with the 0 vector could be linearly independent. So we got to rule out that possibility of 0, right? And now, so theorem 4 implies that this has to be a linearly independent set. And now one more line. We're done, right? Whoop. That was like a moment of profound understanding, right? Whoa! Threw his pencil into the air. How do we want to say this? Basically, we're in R3. We have a set of 3 linearly independent vectors in R3. It's got to be a basis. Any set of 3 linearly independent vectors in R3 is a basis. So u1, u2, u3 is a set of 3 linearly independent vectors in R3, so it must be a basis. And that's a chapter 4 theorem. I don't remember the number. You don't have to give me a number. You can just state that, right? Any set of 3 linearly independent vectors in a vector space of dimension 3 must be a basis. So to me, again, the point of this exercise is it's easy to verify orthogonality, and then we got our basis, basically, just from that. Okay. So part B is to express y, which is this vector, 3, negative 4, 2, as a linear combination of u1, u2, and u3. That means we want to express y as c1, u1 plus c2, u2 plus c3, u3. We need to find c1, c2, c3, those scalars. And that's just our formula. Okay. So I'm just plucking off the formula from the previous page. You're You're going to have to memorize this, and it's really not that scary. It's just the vector y dotted with the first basis vector over the first basis vector dotted with itself. C2 is y dotted with the second basis vector over the second basis vector dotted with itself. Similarly for C3, y dotted with U3 over U3 dotted with U3. Okay, and so this is just plug-in problem. So I'm going to try to do some of these dot products in my head. So tell me if I'm wrong. Y dotted with U1, I'm getting 3 minus 8 minus 4, is that negative 9? Over U1 dotted with itself is 9. So that looks like negative 1. Y dotted with U2 is going to be 6 plus 2 is 8. U2 dotted with itself is that 5? Y dotted with U3, negative 6 minus 20. So I got minus 26 plus 8. Looks like negative 18. U3 dotted with U3 is going to be 4 plus 25, 29 plus 16. 29, 39, 45. Where did my notes go? There. Just in case we all. I get negative 1, 8/5. Yeah. I guess I can make myself reduce that. Okay. So y is equal to negative 1 u1 plus 8/5 u2 minus 2/5 u3. That's what we were after there. So the power of this orthogonal basis is it gives us this formula where we can just figure out what those weights are in the linear combination. Okay, we're going to turn that stuff back on. This kind of calculation we're going to do over and over again. Well, yeah, I think it's worth turning this back on. I hear it. It's coming. Have you, for you guys who've taken 110C, when you start talking about vectors in 110C, just to prepare us for this next step, have you done that parallel perpendicular decomposition, where you take a vector in 110C, you can project it onto another vector. Sometimes we call that like V parallel. And then there's this perpendicular complement, V perp. So V parallel, V perp. That's what we're doing. That's what's going to be going on here. It's really the same idea, but we're applying it to Rn. And we're going to deal with it in a more complicated way because we're going to have more than one dimension that we could be projecting onto. So all right, let's get back into this discussion. But that parallel perpendicular decomposition from 110C might give you a handle on some of this abstract notation we're introducing here. So let U be a non-zero vector in Rn. So it could be any dimension, but I can't draw much more than R3, but we're pretending that's Rn. And we're thinking of U as some vector in Rn. I think in my pictures, I kind of cheat and pretend that U is in the xy plane. Now, officially, U is a point, but sometimes it helps us to think of an arrow to visualize what's going on. And W's the span of U. W's going to be all scalar multiples of that single vector. So W's a line. So a one-dimensional subspace of Rn. Let y bar be any vector in Rn. So in my picture, y bar is kind of floating around. There's a picture on the next page. And again, if it helps you, you can draw an arrow. You don't really need an arrow to carry out this discussion. And what we're going to call y hat is what we get when we project onto this subspace W. So y, that funny looking thing, I call that y hat. Our textbook likes that symbol a lot. That's the projection of y onto W. Now, it does not have to be a line in the xy plane. I'm just also kind of imitating the textbook's picture so we can all be on the same page. But if it is in the xy plane, then this z vector, what we're saying is there's a vector perpendicular to y hat, which you could possibly draw here or here, either, where y hat plus z add back up to the y bar vector. So this is what we're trying to find. We're trying to decompose y into a vector parallel to u and a vector perpendicular to u. So y bar is equal to y hat plus z, and that's just the notation in our textbook chooses for this. This is just the parallel perpendicular decomposition from 110C. Okay. Now, from the way I wrote this, I realized, I was just reading this over this morning, I thought, we don't even know if we can do it. We're just saying we want to do this. We want to try to do this, right? Maybe it's not even possible. So if we could do this, what would be true? Well, y hat is going to have the form Cu, right? Because y hat sits in this one-dimensional subspace where u is a basis vector. All right, so it's defined by, it's all scalar multiples of u. So y hat has to be a scalar multiple of u. And then if this is true, y minus Cu would be our z, and we want z to be in W perp, the perpendicular complement to W. Now, actually, W perp in this picture is like a plane. A two-dimensional subspace, right, of all vectors perpendicular to that line of W. But now my picture's falling apart. Turn the page. So I think I'm just saying the same thing over again. And I guess I also add in a comment here that the length of z can be thought of as the distance from y to W. That's going to be a relevant idea as we go to higher dimensions. And now we want to try to figure out what y hat and z actually are. Like we don't even know if we can find them yet, if such things exist. So I just make an observation. Z dotted with u is going to be 0 because we want z to be in W perp. And and u is in the subspace W, so their dot product has to be 0. From the previous page, we said z can be described as y minus cu. We're still trying to say, can we even find such a thing, right? And so y minus cu dotted with u is 0. And this looks kind of like we did in the proof of that one theorem a little while ago. We want that dot product to be 0, so if we expand it out, we have y dot u minus c times u dot u equals 0. Now these are all real numbers. There are no vectors here. The dot products are real numbers. C is a real number. And so we can solve for c. And so c is y dot u over u dot u. Looks just like that formula with the subscript j, right? Like we're going to see this popping up a lot in the rest of this course. So it looks like I want y hat to be y dot u over u dot u times u. And that's certainly a scalar multiple of u, so that's definitely in the subspace W. All right. And we can just define z to be the y bar minus this y hat vector. And then conveniently, if you add z and y hat together, we're going to get y. And I realized, again, this morning as I was just looking at this point I'd say, well, OK, it looks like we got our c times u for y hat, and here's our z. But to me, it's not 100% obvious that z is in W perp from this calculation. So I feel like there should be one more line here where we actually verify that z is in W perp. I mean, it's kind of implied by all this. But I think it might be worth it for you guys just to verify that z. Now, what would it mean for z to be in W perp? W is a one-dimensional subspace spanned by u. So to be in W perp means z is perpendicular to every vector in W. But we have a theorem that says if z is perpendicular to every vector in a spanning set, then it's in W perp. And U is a spanning set. U all by itself is a one-dimensional basis for W. So what it comes down to is you just got to verify that z dot u is 0. Okay? And so you might say, check this to yourself, write a little note to yourself. That's real easy to show. I mean, we've set it up to be true. We work backwards from that, sort of, right? We wanted z dot u to be 0, so that's where this formula comes from. But so maybe I'm talking in circles here. Maybe it's better I didn't write more on my hand. I tend to write too much anyway. Okay? So let's do this problem. And this is like a plug-in kind of computation. Compute the orthogonal projection of y onto the line through u and the origin in R3. That just means onto the subspace spanned by u in R3, the one-dimensional subspace spanned by u. We're going to write, and then we're going to write y as the sum of two vectors, one in the span of u and one orthogonal to u. I'll leave that up. So the first part of that exercise is just to find y hat, which is y dot u over u dot u. We're going to have a lot of just calculations in this times u. Thank you. That's a vector. This quotient of dot products is just a scalar, so we got to take a scalar multiple of the vector u. And so what's my y dot u here? It's going to be 2 plus 6 minus 15 over u dot u is going to be 1 plus 4 plus 9 times the vector u. Is that negative 7/14 u? Ooh, it came out nice. Negative a half u is 1, 2, 3. So it's negative a half, negative 1, negative 3/2. That's the orthogonal projection of y onto the blah, 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 what that says. Okay. Y hat is what they want us to find. Now, we got one vector. This, so far, y hat is in the span of u. We want to find one vector orthogonal to u. That's z. And the idea is we want our y to be equal to y hat plus z, in this unfortunate notation that you're going to have to try to get used to. So, of course, z is just y minus y hat. So it's kind of anticlimactic finding the z, because we just sort of force it to happen. 2, 3, negative 5 was my y. I'm going to subtract negative a half, negative 1, negative 3/2. So what do I get? 5/2, 4, negative 10/2 plus 3/2, negative 7/2. So there's a z. And so we got y is equal to negative a half, negative 1, negative 3/2, plus 5/2, 4, negative 7/2. And this should be orthogonal to u, or I messed up. So we can check here by dotting the z vector with u, and I'm afraid to do that. Negative 21/2 plus 16/2 plus 5/2. Yes, it works. Yeah, it came out. So you can check that. So I'm just saying check that z dot u is 0, because that's kind of what we were after there. And that really is just your parallel perpendicular decomposition, where you have all those 110C formulas about it, right? Where you probably had to do that on some Math 110C exam. All right, questions? Or? Turn the page back to the handout. So a little bit more vocabulary. I think you're going to like these computations. A little bit more vocabulary. So a set of vectors in Rn is an orthonormal set. So it's a little bit different from the word orthogonal. We've already used the word orthogonal. That means perpendicular. This has the word normal thrown into it. So orthonormal, it's a combination of the words orthogonal and normal. Okay? It's if the set is orthogonal, so it's got to be an orthogonal set, and each vector is a unit vector, meaning each vector has magnitude 1. So we've already seen there's something about an orthogonal set that makes computations come out nice. We can find those scalar weights or components of vectors using an orthogonal basis pretty easily. It turns out if the orthogonal basis is composed of unit vectors, so if it's orthonormal, computations are even easier in life. So in that case, we say that U1 through UP is an orthonormal basis. So what's the most famous orthonormal basis of R3? IJK. vectors, right, in R3, the standard basis. So any standard basis of Rn is already an orthonormal basis. The vectors are orthogonal to each other, are all perpendicular to each other, and they all have magnitude 1. But there are other orthonormal bases. So in R3, if I can, I don't think I can do that. Can't bend my fingers anymore. But, you know, any triple of vectors pointing in any direction that are all mutually perpendicular and all of length 1 form an orthonormal basis for R3. So it isn't like IJK or the standard basis are the only ones. All right. Also, this fact you should know, we're not really going to have to work with this too much. But any orthogonal basis, or any orthogonal set of non-zero vectors, can be converted to an orthonormal set. You simply multiply each vector by the reciprocal of its length. You just convert those to unit vectors in the same direction, right? Which is a process I think you're familiar with. I'm not going to ask you to do this because it's very tedious and messy, and it's just easy and kind of obvious. So I just want you to know that fact. We're usually just going to stop with an orthogonal basis. But like way back when I was a student, they made us like do tests with 10,000 problems on them, and we had to rush as fast as we could and do billions of fraction calculations. They'd always say, oh, you have to find the orthonormal basis. So we'd have to divide by the magnitudes of all those vectors. And of course, we'd all make mistakes and get all the answers wrong. So just be aware that that's not a difficult thing to do, really. And I'm not going to ask you to do it. And there's just a little theorem here I made up that is sort of obvious, but I felt like it's necessary to verify this, that if u and v are orthogonal vectors and you take scalar multiples of them, the results AU and BV are still orthogonal, right? That should make sense. So if you have two perpendicular vectors and you take scalar multiples of them, you still have two orthogonal vectors, right? That's the end of 6.2. So we got time to start some 6.3 and get back on track a little bit with the schedule. And okay, 6.3. This is really the heart. This section and the next section are the heart of this chapter 6. So once we get through 6.3 and 6.4, we're going to start applying these ideas to some interesting situations. And so it looks like such a mess. So my job is try to convince you that this isn't as complicated as it looks. This example we just did here is kind of like the heart of the matter. But that was with a one-dimensional subspace, right? What we're going to talk about now is what if we have a higher dimensional subspace of Rn, so that subspace W has some basis, U1 through UP, an orthogonal basis. So W, I guess, is p-dimensional here. Then every vector in Rn, so y might not be in W, probably isn't in W. Y is just in Rn. Y can be decomposed as a sum of two vectors, can be written as a sum, where y hat is in W, the subspace, and z is in the perpendicular complement of the subspace. And that can only be done in one way. So that's not so obvious to me, that there's only one possible way. So there's something special about breaking a space into a subspace, breaking Rn into a subspace, and the perpendicular complement of that subspace. So there's a unique way to describe vectors in Rn as a sum of vectors from each of those two. And this is how you do it. This formula tells us exactly what y hat has to be. And then just like we did in the previous exercise, z is always going to fall out. We're always going to be able to compute z by taking y minus y hat. Now, you're like, oh my God. If you cover everything up with the first term, That's what we just did in the previous exercise, because we were working with a one-dimensional subspace. So if you can handle that y dot y1 over y dot u1 over u1 dot u1 coefficient, basically we're just doing the same thing for each one of the orthogonal basis vectors of the subspace, right? Now, why is this true is something we'll talk a little bit about, but that's going to be the heart of what we need for our calculation. By the way, if y is in W, y hat will equal y, and so z will be 0. So this holds just as well for vectors in W as vectors not in W. So just want to say a little bit with a picture. So go back to the picture we had before. What's the same and what's different? So again, I'm using a very simple situation, but again, W could possibly be a two-dimensional space with basis vectors U1, now I got to extend my plane a little bit that way, U2, where they're perpendicular to each other. And y is just going to be some vector out here. And what we're saying is y can be uniquely described. There's only one way to describe y as a y hat plus a z vector. I guess I can imagine z. My picture here, I want to go a little higher, right? Now, if W is a two-dimensional subspace of R3, W perp is just going to be a one-dimensional subspace, so it would be the z-axis. I can't get beyond 3 dimensions in a R3 kind of situation. And so what we see is y is equal to y hat plus z. So it's very similar to what we just did, but I just want you to think about how that W could be a more complicated subspace. And y hat will be some linear combination of the u1, u2 basis vectors. And this is exactly the linear combination it's going to be, as set by that formula. And it's really the orthogonality of the uj vectors that makes this whole thing work. We're going to talk about the proof a little bit, and I think we won't get to the exercise, but let's talk a little bit about the proof of this theorem. Let y be a vector in Rn. Define y hat as above. Just use that formula. Say that's what y hat is going to be. Clearly, y hat is in W, right? Why is y hat in W? Because y hat is a linear combination of the u1 through up. Those are the basis vectors for W, right? Now, we claim that z is in W perp. So to me, that's what's not obvious. We know y hat must be in the W space, but why is it automatically true when we take this difference that we get a vector z that's perpendicular to W? See, like it's not, geometrically, it's not clear to me that the z vector wouldn't be tilted a little bit. Like, why does it have to be straight up and down in this situation? Right? It's not obvious. So what we do is, to verify that, we dot z with, I guess, u1 to start out with. Now, z dotted with u1 is going to be y dotted with u1 minus all that stuff dotted with u1, because z is just y minus all that stuff. Y dotted with u1 minus, I just expand the whole thing out. This term doesn't drop out, but we have some constants that cancel. So this term we stays. This, we have some canceling. All the remaining terms are going to drop out because they all involve dot products of different u vectors, u1 with u2, u2 with u3, or whatever, I guess u1 with different vectors. And that's an orthogonal set. So this is where the orthogonality makes things work out. And it leaves us with two terms that are just opposites of each other. So that's 0. So z dot u1 is 0. We can go down the line and show that z dot u2 is 0 all the way down the line. So it's not that hard to show that z is orthogonal to each uj. We set it up that way. And so z is in w perp. And now there's another important idea here that this can only be done in one way. That's what we mean when we say we have to show that y hat and z are unique. Like maybe there's another vector here and another z that add up to y. Maybe there's more than one way we could do this. And so turn the page. So what I'm saying is suppose we have y equals a different y hat, y1 hat, and a different z, z1 bar. Then, turn the page. Then these are both equal to y. Y is equal to y hat plus z, y1 hat plus z1. And so I can subtract, juggle things around, and write that as y hat minus y1 hat equals z1 bar minus z bar. And now y hat minus y1 hat is in w. Those are both in the given subspace w. z1 minus, oh, typo. z1 minus z must be in w. That's a typo. Sorry. Let's see. Can I do the magic of multimedia? Oh, I haven't cut that one before. Zoop. Right there. You see it? Sorry about that. And it's kind of obvious because in the next line I say since. Oh, no. I'm sorry. That's not a typo. Take that back. I take that back. Sorry. I just spaced out there. No, that's absolutely true. Y must, sorry. That's w. Y must z1 minus z be in w. It goes with this line. This should be so, S-O. z1 minus z is equal to y hat minus y1. Sorry. So that's perfectly OK the way it was written. And maybe I just want to make sure you don't have the same brain slip I had. So I'm just saying z1 minus z is equal to y hat minus y1 hat, which is in w. So that's got to be in w. But again, the thing is z1 bar minus z bar is in w perp, because we verified that on the previous page.
Isn't that saying the same thing in the second line and the third line? z1 minus z must be in w, and since z1 minus z is in w.
Perp, we have z1 minus z is in the intersection of those two. So the argument is z1 minus z has to be in both w and in w perp. It's in w because it's equal to this difference. OK, I must be going over time because everybody's putting their stuff away. And it's in w perp because of the argument on the previous page. Yeah. But the intersection of those two is only 0. So this difference has to be the 0 vector because it's in both. And that means z1 equals z, which means there's only one of those. And then also y hat minus y1 hat is 0, so y must equal y1 hat. OK, done. All right, sorry. But that was perfectly OK as written. Sorry, that wasn't a typo. All right, see you next time, Friday.